All right, strap in, everyone. Today's deep dive, well, we're going right to the heart of how computers think, the Turing machine.
Yeah.
I know, I know. Sounds like some ancient computer science relic, right?
Maybe. Maybe.
But stick with me here. This thing, this Turing machine, it's way more than just history.
Oh, yeah.
It actually helps us, even today, to grasp what computers can and can't do.
Interesting. What's fascinating is the Turing machine, it acts like it's like a blueprint almost for what computation can even do, the limits of it.
So we're not just, dusting off old textbooks here. This has, like, real implications for the tech we use every single day.
Oh, absolutely.
Wow.
And it all sprung from a remarkable figure, often called the father of computer science, but his story, I mean, it goes way beyond that. He played a crucial role in breaking the German Enigma code.
No way. During World War II.
Yeah.
Wow. Talk about high stakes, huh? Okay, you got me intrigued, I'll admit it. So let's break this Turing machine down. What exactly are we talking about here? Like, in simple terms.
Okay, picture this. An infinitely long tape.
Infinitely long, okay.
And it's divided into cells. Each cell can hold a symbol, a 0, a 1, even just a blank space. Think of the tape like the machine's memory.
Okay, got it.
Then you've got a head that can move along that tape. It reads and writes those symbols.
Okay, so I'm trying to, like, visualize this. Is it kind of like a librarian?
Yeah.
Moving along an endless bookshelf, scanning and updating records?
That's a great analogy, yeah.
Okay, cool.
Now, add in a set of states that the machine can be in,
Okay.
and a set of rules
Rules.
that dictate what to do, based on what symbol the head reads and the current state it's in. So, for example, let's say the machine is in state A,
State A.
and it reads a 0.
Reads a 0.
It might write a 1, move the head to the right, and switch to state B. Like a simple set of instructions, almost like a basic code.
So it's kind of like a set of steps then that it follows, like based on what it encounters.
Right. Exactly.
Okay, I think I'm getting that. But how does something so seemingly simple underpin the power of modern computers? Like, that's the part I'm not.
It's pretty incredible.
Yeah.
Those simple components, the tape, the head, the states, the rules, they can actually simulate any computation that can be done by any computer. It boils down the essence of what an algorithm is, a step-by-step process driven by inputs and rules.
Hold on. Are you saying that my smartphone, with all its apps and processing power,
Yeah.
it's fundamentally doing the same thing as this theoretical machine with an endless tape?
Yeah.
Really?
You got it. That's the beauty of the Turing machine. It distills computation to its very core. Real computers, of course, they're much more complex in their architecture and operation, but the underlying principle is the same. They take in data, process it based on instructions, and then produce an output.
Wow, I never thought about it like that. Okay, so can you walk me through an example? How does this Turing machine actually work in practice?
All right, so let's say we have a Turing machine designed to add 2 numbers.
Add 2 numbers. All right.
We'd start with those numbers represented on the tape, separated by a blank cell.
Okay.
The machine would begin in its starting state, read that first number, move to the right, read the next number, and then by following its rules, it would write the sum of those 2 numbers on the tape. And finally, it would transition to a specific accepting state.
Accepting state, huh?
Which indicates that the calculation is complete.
Oh, I see. So each action is determined by the current symbol and the machine state, like a recipe for calculations.
Exactly. And that's how every algorithm works. From sorting information to displaying images on your screen, they're all built upon this concept, this step-by-step process guided by rules.
This is making me rethink everything I thought I knew about computers. But okay, so why is the Turing machine so important? Like, is it just a cool theoretical concept? Or does it have, like, real-world significance?
This is where things get really interesting. The Turing machine isn't just about how computers function. It also defines the limits of what's possible with computation.
Okay.
And that's where the Church-Turing thesis comes in.
The Church-Turing thesis. All right, I'm all ears.
This thesis, it basically states that anything computable by any machine, any computer we can imagine, even ones we haven't invented yet, they can also be computed by a Turing machine. Just let that sink in for a moment.
Yeah.
This seemingly simple model, it captures the essence of what all L computers, algorithms, programs are capable of achieving.
That's incredible, but also a little unsettling. Does that mean there are problems that no computer can ever solve, no matter how advanced they become?
That's precisely what it means. There are certain problems that are undecidable, meaning no algorithm and therefore no Turing machine can ever solve them. A famous example is the halting problem.
The halting problem, okay.
Yeah, it asks, given a program and its input, will that program eventually stop running or will it loop forever? Seems like a straightforward question, right?
Yeah, it does.
But Alan Turing proved that no algorithm can solve this, not for every possible program and input.
So even with like the most powerful computers we can dream up, there will always be problems beyond our reach. That's both fascinating and humbling at the same time.
Absolutely. The Turing machine, it highlights that even in our increasingly digital world, there are boundaries to what computation can achieve. And it helps us identify those inherently unsolvable problems so we're not, chasing after solutions that simply don't exist.
So the Turing machine isn't just about what computers can do, but what they can't. It's like a map of the computational universe, showing us the edges of what's even possible. I'm already feeling like I need to take a break and process all of this, but I'm hooked.
Back again.
I am ready for more Turing machine insights.
You got it.
This whole deep dive has really like flipped my perspective on computers. I used to think of them as, magical boxes, could do anything. But now I understand they're intricate systems operating within like these fundamental limits.
Yeah, exactly. And those limitations are what make the Turing machine so relevant. Even today, it's not just some, historical artifact. It's a tool for understanding the boundaries of computation.
Okay.
In fields like artificial intelligence, for example.
AI. All right, now we're talking.
Yeah.
I've always been so fascinated by the idea of machines that can think like humans.
Yeah.
But is that even possible? Does the Turing machine shed any light on that?
Well, that is a question that has sparked countless debates.
I bet.
Some argue that since a Turing machine can simulate any computation, then a sufficiently complex machine could, in theory, replicate human thought processes.
So we could potentially build a Turing machine that's as intelligent as a human.
It's a possibility. But, gotta remember, the Turing machine, it's just a model.
Right.
It doesn't give us a blueprint for building such a machine or tell us how complex it would even need to be.
Right.
And then there's the bigger question, is replicating computation truly equivalent to achieving intelligence?
Yeah, that's a deep one.
Yeah.
Can intelligence really be like reduced to algorithms, computations?
Right. Some believe that consciousness, intuition, creativity, those things are fundamentally different from the logical processes that a Turing machine can perform.
So even if we built a machine that could pass the Turing test, convincing a human that it's also human.
Yeah.
Would that truly mean it's intelligent?
Yeah, that's the crux of the debate. The Turing test, it's an interesting concept, but it doesn't necessarily address those deeper questions of consciousness, subjective experience.
Wow, the Turing machine opens up like so many thought-provoking avenues. It's raising as many questions as it's answering.
It certainly does. That's what makes it such an enduring and fascinating concept. It makes us think about the nature of computation, intelligence, those boundaries of what's even achievable.
Okay, so we've talked about how the Turing machine helps us understand what computers can and cannot do.
Yeah.
But I'm curious about its practical impact.
Yeah.
How does it influence the way we actually design and program computers in the real world?
Well, we don't actually build physical Turing machines.
Right, with the infinite tapes?
Yeah, with infinite tapes. But its principles are deeply ingrained in how we design modern computers.
Okay.
For instance, the concept of a CPU, the central processing unit. That's essentially based on the idea of a Turing machine's head, fetching and executing instructions.
So the CPU is like the computer's brain. It's constantly reading and processing instructions.
Precisely. And then the computer's memory, where the data is stored, that's analogous to the Turing machine's tape. Modern computers, obviously, they don't have infinite memory.
Right, thank you.
But the principle of storing and retrieving information, that's the same.
So it's like the Turing machine. It provides like a foundational blueprint for how computers work, even if like the actual implementation is much more complex.
Exactly. And beyond just hardware, the Turing machine's influence is evident in the development of programming languages, algorithms.
Oh, okay.
For example, the concept of a loop in programming, where a set of instructions is repeated until a condition is met. That's directly inspired by the Turing machine's ability to move back and forth on its tape, processing data in a cyclical manner.
So the way the Turing machine operates has actually shaped how we write the instructions that tell computers what to do.
Yes. It's also been instrumental in developing tools and techniques to analyze how efficient algorithms are. Remember we talked about computational complexity?
Yeah, yeah.
The Turing machine, it provides a framework for classifying problems based on the time and resources required to solve them.
Right. So it helps us determine whether an algorithm is going to be like a quick sprint or a never-ending marathon.
Precisely. This is critical for optimizing code, making sure programs run as efficiently as possible.
Man, I'm starting to get just how profoundly the Turing machine has like shaped the entire landscape of computing. It's not just some theoretical concept. It's the foundation upon which so much of our digital world is built.
And it all stems from Alan Turing's remarkable insight that even the most complex computations can be broken down into a series of simple logical steps.
It's incredible how such a simple model can have such a profound impact on technology, science, even philosophy. This deep dive has been mind-expanding.
I agree. The Turing machine is a window into the very nature of computation. And its implications, they just continue to ripple through our digital world.
Man, I feel like we've covered so much ground in this deep dive. You know, from the theoretical foundations of computation all the way to the real-world implications of the Turing machine. It's amazing how this one concept connects so many different ideas.
And what's even more fascinating is that the Turing machine, it continues to inspire like new areas of research, exploration. There's a growing field called unconventional computing.
Unconventional computing.
Okay. It's pushing the boundaries of what we traditionally think of as a computer.
Unconventional computing. That definitely piques my curiosity. What's that all about?
So researchers in this field are exploring alternative ways to perform computation, inspired by things like biological systems, quantum mechanics, or even the laws of physics themselves. They're looking for ways to solve problems that are inherently difficult for traditional computers, like simulating complex biological processes or designing new materials.
So they're essentially trying to like break free from the limitations of the Turing machine.
It's not necessarily about breaking free. It's more about expanding upon the concept.
Okay.
Remember, the Turing machine, it defines the limits of what's computable, but it doesn't dictate how those computations have to be carried out. Unconventional computing is about exploring new ways to implement those computations.
Okay. Yeah.
Using different physical substrates or principles.
That's a really interesting distinction. So what are some examples of these unconventional computing approaches?
Well, one fascinating area is DNA computing.
DNA computing, okay.
It uses strands of DNA to perform calculations.
Wow.
DNA molecules, they have this incredible capacity to store information and interact with each other in very complex ways, making them potentially very powerful computational tools.
Wow. Using DNA to compute. That sounds like something straight out of like a science fiction movie.
It does, doesn't it? But it's a real area of research.
Wow.
With some very exciting potential applications. For example, DNA computing could be used to develop new diagnostic tools or even personalized medicine based on an individual's genetic makeup.
That's incredible. So even though the Turing machine was conceived, decades ago, it's still shaping cutting-edge research today. It's truly a foundational concept.
Absolutely. And that's what makes studying the foundations of computer science so rewarding. It gives you this framework for understanding not only where technology has been, but also where it might be heading.
I completely agree. It's like having a roadmap of the computational universe.
Yeah.
It's guiding us as we explore these new frontiers.
And who knows what incredible discoveries await us on that journey.
Yeah.
Perhaps one day we'll develop computational systems that even surpass the capabilities of the Turing machine itself.
Now that's a mind-blowing thought, to think that we might one day create something even more powerful than the model that defines the limits of computation.
It's certainly a possibility, and it's that sense of possibility, of pushing beyond what we know that makes the study of computer science so captivating.
Well, I think it's safe to say that our listeners are going to be pondering the implications of the Turing machine for a long time to come. This deep dive has given me a whole new appreciation for the power and the complexity of the digital world we live in.
I couldn't agree more. It's been a pleasure exploring these ideas with you.
And to all our listeners out there, we'll leave you with this. What will you compute today? Whether it's writing a line of code, analyzing data, or even just, using your smartphone, remember that you're interacting with a system built upon the foundations laid by Alan Turing and his remarkable Turing machine. Thanks for joining us on this deep dive into the heart of computation.